velocity-dependent forces, I want to take a look at 3 cases of two-dimensional motion. First, our normal two-dimensional motion. So no air drag, just the gravitational force pulling it down. Second, motion with a linear drag, so the drag force is proportional to the velocity in the opposite direction. And then third, quadratic drag, so the velocity is the force, oh, that's a vector. So the vector force, the drag force, is some constant c, velocity squared in the opposite direction of velocity, so we have that unit vector v hat. And what I want to do is to look at these 3 cases for the classic demo of all time. What happens if you shoot a ball horizontal and drop a ball at the same time from the same position? Which one hits the ground first? So I'm going to show you without air resistance, they hit the ground at the same time. And then we'll explore if that happens for these other 2 cases. Okay, so that's what we're going to do. Let's start with projectile motion. And I know it's not a velocity-dependent force, but we got to start somewhere. So I'm just going to erase all this stuff. And let's just deal with an object launched with an initial velocity v of 0 equals v0. Well, no, I'm not even going to do that. Let's just say I have an object that's launched. It doesn't really even matter. So I have an object. It's moving, and it has some velocity v, which is vx x hat plus vy y hat. So that's my velocity. Okay, I'm going to use that same thing for the other cases too. Let's go ahead and write Newton's second law. I shouldn't draw that force, that arrow on there. Let's just put it like that. So I have the downward gravitational force. So Newton's second law says F net is going to be the net force. In this case, it's just mg, which is a vector, and that's ma. Let's write this as 2 scalar equations, one for the x direction and one for the y. And I'm going to use normal x and y like that. Okay, so I get the net force in the x direction is going to be the net. This is the only force. It has no x component, so it's going to be 0 x hat is equal to max. So that's my x equation of motion. I could take that. I can integrate twice to get position as a function of time. I'm not going to do that. The y equation, the y component of this is negative mg. That's the y component, is equal to may. That's the y component of a force. That's a y differential equation of motion. I could integrate this twice and get y as a function of time. So this tells me that the 2 balls are going to have, if they have the same y conditions, they're going to have the same. That's cool. I didn't do that before. The same. I'm kind of. This is getting me. See if I do double thumbs. Nope. Just one thumb. Okay. If they have the same initial y conditions, they're going to have the same y equation of motion. So if I go over here, and there's no dependence on x, right? So if I go over here, these 2 balls, I shoot one horizontally and I drop one, they have the same y of 0 is 0. They have the same y of 0 is h. So they're going to have the same y motion. So if in this case, they're going to hit the ground at the same time. We kind of already knew that, right? We took earlier physics. The introductory physics said, yes, that would indeed happen. Okay, now let's look at linear drag. Let's do the same thing. So in linear drag, I have this. I'm going to say my velocity right here, v is vx x hat plus vy y hat. I have a downward gravitational force mg. Let's go ahead and write that as 0 x hat minus mg y hat. That's that force right there. And then I have a linear drag fd. So I'm going to say fd is equal to negative bv, but there's my v, right? So this is going to be negative b vx x hat minus b vy y hat. So, vy could be negative, and that would make the y component of the force positive. So that's all fine. Okay. Now, let's do again net force in the x and y direction. So here's my Newton's second law, F net in the x direction. Well, what forces are in the x direction? It's going to be this plus this. So I have 0 plus negative b Vx. So negative b Vx, and that's going to be equal to the mass times the acceleration in the x direction. If you want, you can write that as mass dvx dt. That's the way we would do that, right? Now I'm going to write, but that is my differential equation of motion. Now I'm going to do the same thing over here. F net in the y direction is going to be equal to this value, negative mg, minus bvy equals may. I don't really care about that part. Equals m dvy dt. Okay, so let's just rewrite these two equations because they're the most important things. This one, I have negative b Vx equals m dvx dt. We already solved that equation. We just called it v. We said an object moving with in the horizontal direction with no gravity. We did that problem. I'll link to it down below if you missed it. Okay. Over here, this equation looks like this. Negative mg minus b vy equals m dvy dt. We did that equation too. That was an object that's falling vertically, right? And so you'll notice here, Vx. I could solve this for Vx as a function of t. I did. I just didn't have the x there. Vy. There's no x's. So I could solve that for an equation of a function of Vy as a function of t. Now, yes, when we did this earlier, I called down positive, and then that's one trick. And the other trick is to use terminal velocity here and get a u substitution. But that's just a trick. It doesn't really matter. The key is that's a differential equation that does not depend on x. That's a differential equation that does not depend on y. So I have two independent equations. So now, again, when I drop the two balls, so that one starts off with initial velocity in that direction. That one has 0 direction. But in the y direction, that has a 0 y velocity. In the y direction, that one has 0 y velocity. So in terms of this equation, those two have the exact same equation because it doesn't depend on the x velocity. So the two balls would still hit the ground at the same time, even with air resistance, if it's linear drag. And I'm going to show you this stuff in Python, just so you know. Okay. I'm trying to think. Yeah, I'll show it to you. Okay. So, and there's going to be some coding, but that's fine. Now, let's go on to quadratic drag. So I still have the same velocity. I'm going to erase this stuff. I have a different drag force. And we're going to have to do a little bit more work here. So my drag force, I'm going to write this as negative c magnitude of the velocity squared v hat. So when we square the velocity is a vector, so I can't just square it, right? So I have to take the magnitude of it and then square it. And that is a scalar, that's a scalar, so I have to include the unit vector v hat in order to make this back into a vector. That's kind of a big deal. Okay, so but we need to write this as a whole vector, so let's do that. Let's go over here. I'm going to write the magnitude of v is going to be equal to the square root of vx squared plus vy squared. That's how we find the magnitude of a vector. And then I can write v hat is going to be the vector v divided by the magnitude of v. I can write that. V hat is going to be vx x hat plus vy y hat over the square root of vx squared plus vy squared. And so in this case, I'm dividing that by this and this by this, but I wrote it as one thing because I don't think it really matters too much. But that I can write as my expression. So let's just put this all together, and I have f drag is going to be negative c, v squared is going to be this squared, so I get vx squared plus vy squared. and then I have to multiply by v hat. So it's going to be vx x hat plus vy y hat, and then I'm going to divide by this. So I can put that over here. Divided by the square root of vx squared plus vy squared. Okay, so I can simplify this because I have this and the square root of that. So this is just going to be a square root up here. So let's write this as negative c square root vx squared plus vy squared. That's a y. I have my trouble with my y's. And then I have vx x hat plus vy y hat. I mean, maybe you can already see where we're going, okay? But if you can't, just hold on because we're going to get there. Now I can write Newton's second law using this and my gravitational force, negative mg y hat. So let's write down the x equation of motion. I can erase that. F net x equals m dvx dt. Sorry about that. Okay, so that's my acceleration. Now what are my forces in the x direction? Well, I have no gravitational force. So that's zero, the zero component of the gravitational force. But I do have an x component. So it's this, right? So it's going to be negative c times this times vx. So it's going to be equal to negative c square root of vx squared plus vy squared times vx. That's my x equation of motion. Yes, there's a problem. Let's write down the y equation of motion. F net in the y direction is going to be m dvy dt. And that's going to be equal to the gravitational force, negative mg, that's in the y direction, plus this y component, which is going to be this times that. So it's going to be minus, I need to erase this stuff. Minus c square root vx squared plus vy squared vy. We solved for the equation of motion for an object moving with quadratic drag and no gravity. It did not look like that, right? It just had the v squared. We solved for the motion of an object moving with gravity. It was really tough with quadratic drag, but just moving up and down. It did not look like that. Because you'll notice here in my x equation, I have a y. In my y equation, I have an x. So I don't have two independent equations, one that only depends on y and one that only depends on x. So right there you can see if I take two objects and I launch that one horizontally, they start with the same initial y conditions, but the y motion here depends on its x motion, whereas that one does not. So if there is quadratic drag, they do not hit the ground at the same time, and we're going to show that. Okay, so now let's show that, because this is like really hard to solve. We can solve this numerically using the normal Euler method of breaking things into small time intervals. I've said that so many times, I'm going to assume that you've seen one of my videos that does that. I don't want to talk about that. I'm just going to go ahead and jump in and do this. So I'm going to plot a whole bunch of stuff. I'm going to plot the x and the y. I'm going to just plot trajectory. Let's plot trajectory for three objects. One that has no air resistance, one that has linear drag, and one that has quadratic drag. And then we can see what happens. I guess if I plot the trajectory, I guess I need to plot the x and the... I'm trying to decide what I want to plot. Do I want to plot like two falling balls? I could even animate it. I'm trying to decide what to do. Let's see if I plot. I'm thinking if I plot y as a function of time, I could do 6 balls, right? Because I have, well, those two, let's just do it, let's just do I'm just going to do quadratic drag. I'm going to model this with quadratic drag. I've already done the other stuff before. I'm just going to plot these two balls. One's thrown horizontally and one's dropped. And then that'll be a little bit more simpler. And it's going to get too complicated otherwise. OK, jumping over to Python. I've already picked some values here for my conditions that I thought would work. Well, let's just go ahead and make two graphs. I'm going to do two trajectories. And I'll animate them in real time. That will make everything fair, right? Okay, so let's make a graph. One graph, it's going to be a trajectory. G1 equals graph. Title equals quadratic drag. That's fine. X title is going to be equal to X in meters. I guess I should be right. Y title is equal to Y in meters. And then my width is going to be 400, height 200. And then I'm going to have two graphs. A is going to be my drag force. It has air. G curve. Color equals color dot blue. Label equals drag. And then I think this dot equals true will make it leave a dot. I'm not sure if that's the right syntax. If it's wrong, that's fine. I'll fix that later. And then FG is going to be G curve color equals color dot red. Label equals no air. No. I'm sorry. Let's just call this F1 and F2. F1, F2. And in fact, I only need to plot the Y motion. But we're going to do trajectory anyway. So this is going to be horizontal shot. And it's going to be dropped. That's right. That's what I want. And then I'm going to put dot equals true. It might be marker. I can't remember. OK. So I picked my mass. I picked my coefficient c. I picked my initial velocity v. But I need to have two positions. I need to have two velocity vectors to start off with. And then I can go from there. So let's start off. We're gonna use vectors. I'm gonna start off with my g vector, vector 0, negative 9.80. I'm going to start off with my position. Let's say h is, it's 2 meters per second launched off of a 1 meter thing. So h is 1. R1 is going to be my launched object, and it's going to be a vector 0, h0, right? And then R2 has the same initial position, 0, h0. And now for the initial velocities, v1 is going to be equal to vector v0, 0, 0. It's going to be launched horizontally. And the other one is just going to be dropped. v2 is vector 0, 0, 0. OK. Now I need my time. T equals 0. dt equals 0.01. I think that should be enough, but who knows? We'll see. And I'm going to run this, let's just say, while t is less than 1. For now, let's say 0.5. And that's going to be, that's short. So let's say that's 0. That'd be fine. Rate 1,000, right? So rate tells me how fast I do the calculations. Now I can calculate the force on object 1. So F1 is going to be equal to, I'm going to do all this in one step. M times G, that's my gravitational force, minus C times V squared. So V squared, I need to take the magnitude of V1, that's my velocity. So I'm going to say mag V1, and then I need to square it. That's not a vector. So I'm going to multiply by a unit vector, which is norm V1. There's my force. F2, let's just be equal, is M times, it's the same thing, right? The only difference is that one doesn't have a velocity. But this is going to be V2. V2. OK. Now I can calculate, let's just do the update the velocity. So V1 equals V1 plus F1 times dt over m. They have the same mass. V2 equals V2 plus F2 times dt over m. Now I need to update the position. R1 equals R1 plus V1 times dt. R2, oh, not 42. R2 equals R2 plus V2 times dt, and then update time. T equals T plus dt. Now I'm going to update my graph. So remember, I'm plotting y, x versus y. Is your trajectory. F1 dot plot my x coordinate, which is going to be R1 dot x versus my y coordinate, R1 dot y. And the same thing for F2. R2 dot x, R2 dot y. And that should do it, but you never know. Okay, let's just run it. I didn't even save it. Okay, that worked. Now, the question is which one got to the ground first. Neither of them, because I'm only at 0.4. So this one is ahead of that one. So let's run this until the bottom one gets to the ground first. I'm going to run this, change this time up here. While R2.y is greater than or equal to 0. So this will stop when that first one gets to 0. And the dot thing equals true did work. So this is kind of interesting. That curve is really interesting. In this case, it looks like it reached terminal velocity. It completely slowed down in the horizontal direction, which is fine. I'm going to change that. But this one got there a little bit faster. You see, when this one stopped, that one's not quite at the bottom. Okay, so it did get there first. Let's decrease the drag to make it more interesting. I'm just put that at 0.1, see what happens. That looks a little bit better. But then again, you see the drop one gets to the ground first. And so if we go back to the code, the board, let me switch up here to the board. Why does that happen? Well, in the x direction, I have an x velocity and a y velocity. So if I drop it, then it has no x velocity, so the drag force is smaller. So that means that it's going to have a greater Why did I get rid of the, oh, that didn't have a, I'm sorry. In the drop case, I'm over here. In the drop case, it has no x velocity, so it has a smaller drag force. So this thing is going to slow it down less. In the other case, having a large x velocity makes it go a lot slower, even in the y direction, because of that term right there. So that's why the drop ball is going to hit the ground first. If you have quadratic drag, that's not true if you have linear drag. Let's just show. I'm going to show you really quick if it's linear drag, they hit the ground at the same time. I can do that because I can just really quickly change the force. And I'm not even switching on the computer. Okay, sorry about that. So back to the computer, I have a drag force B. Let's put that at, that's fine, 0.5. So all I need to do down here is to change this force. I'm going to actually comment these out in case you don't want to get rid of those. And F1 is m times g minus b times v1. That's it. I don't have to find the magnitude. I don't have to find the unit vector because v1 is already a vector. F2 equals m times g, oh, what the heck, minus b times v2. Now, oh, I'm having some issues here. Nah. Okay, so let's run that and see what happens. Do they get the ground at the same time? Identical. So with linear drag, they do. So that shows it. I'm pretty happy with that. There you go. That's it for my classical mechanics, velocity-dependent forces. Next thing, just I want you to, if you want to know, next thing I'm going to go on to work energy. So I'll see you in work energy. We're going to do work energy line integrals. It's going to be great stuff. Okay, that's it.